Hi, everybody, and thanks for attending this presentation on Ethernet for 5G fronthaul and Open RAN. My name is Sebastien Prieur, and I'm Product Line Manager for 5G and fronthaul at Exfo. Glad to be here and honored to share the stage with the other panelists. So where are we with 5G, and what are the main drivers for next-gen transport? So first phase of 5G is well underway all around the world, with many 5G network already in operation and many more to come in the next few months. And we are now at the stage where 5G will scale to volume to support more users, to support the never-ending increase in bandwidth demand. Operators now need to densify their transport network dramatically with more fiber, more cell sites. And this is taking a toll on the transport layers and driving the need for more capacity and higher speed at the access and the aggregation layer. We are also entering the second phase of 5G with a transition from 5G NSA to 5G standalone and the introduction of the 5G core. And this is the point where we will get the full 5G with the support of low latency communication and new applications like industrial IoT. This is where edge computing come into play. And this is a point where the transport infrastructure will have to support low latency and network slicing. And then another trend is around the push toward network synchronization. The fact is that timing is critical for 5G, and we see more and more adoption for 1588 PTP and SYNCI by the operators as the main solution to synchronize their 5G network in frequency and in phase. And last but not least is Open RAN, as the operators are aiming for a more open, intelligent, and virtualized RAN ecosystem. There is now a clear momentum for Open RAN technology with organizations like ORAN Alliance and TIP actively working on open specification and reference design. Very good support from the operators here with strong commitment from many of them to deploy ORAN compliant technology in the next few years. Let's take a step back and look at some of the key difference between 4G and 5G RAN architecture. So we've seen a few years ago the introduction of fiber link between the remote radio head and the baseband unit, replacing long coaxial cable to the antenna in a distributed RAN architecture. So this step has been followed by a move to the centralized RAN architecture, or CRAN, not everywhere, but in some markets, some region. We see the centralization of the baseband unit in central office or BBU hotel. And this created a layer called the fronthaul, with eCPRI being the main protocol for fronthaul interface. And on the other side of the baseband unit, we have the backhaul, which is the aggregation layer connecting the BBU, the baseband unit, to the mobile core, and typically relying on IP and Ethernet. Now 5G is introducing few key changes. The remote radio head is now called a radio unit, and the BBU is now separated into two entities called the DU, or distributed unit, and the CU, the centralized unit. The split between the DU and the CU introduce a new interconnection layer called the middle. So the advantage of this split is to keep some key functionalities close to the radio unit while opening the possibility to virtualize and centralize the CU. The middle is very similar to the backhaul using IP and Ethernet protocol, but for the fronthaul, we have a new protocol called eCPRI. And eCPRI is a packet-based protocol. So eCPRI stands for Enhanced Common Public Radio Interface, and is the fronthaul protocol that is replacing CPRI and UPSI in 5G network. eCPRI was initially developed by the eCPRI Forum, and it is now used and enhanced by the ORAN specification. eCPRI implementation is over Ethernet 10 gig and 25 gig, but could evolve to higher rate, like 50 gig or 100 gig. And as it is a packet-based protocol, the bandwidth can scale according to the user plane traffic, making it much more flexible than CPRI. And eCPRI is also supporting several functional split between the radio unit and the distributed unit, which help optimize the efficiency by reducing the amount of traffic that need to be carried over the radio and the DU. And eCPRI is a packet-based protocol relying on Ethernet, but best effort Ethernet is not good enough for the fronthaul. We need a more deterministic behavior to guarantee that critical traffic will have the required priority. So this is where IEEE time-sensitive network, TSN, come into play with specification 802.1 CM specifically for the frontal that have been ratified. And another important piece is ORAN. ORAN objective is to transform the radio access network industry toward open and fully interoperable RAN. So ORAN is making sure that the equipment from different RAN vendor will be interoperable together. And to achieve this, ORAN came up with a set of specifications for open interfaces for the frontal and the middle. An ORAN open frontal specification is defining a user plane, a control plane, a management plane, and a synchronization plane, and is based on eCPRI for the control and the user plane, and is defining also a specific split of functionality between the radio and the distributed unit, which is the split option 7.2x. And there is not a one-fit-all topology for the RAN. Multiple scenarios need to be supported. Different scenario of CRAN or centralized RAN with the DU and CU that could be either co-located or separated and hosted in two different data centers. Scenario 3 is particularly popular for millimeter wave radio integrating the RU and the DU, and where we have a middle connection up to the radio. And then the classical DRAN approach with backhaul up to the cell site where the DU and the CU are co-located. So still widely used in 5G in low band and mid band spectrum. And the transport infrastructure need to evolve, as in many cases, operators will eventually have to deploy a mix of these topologies over the same converged transport network. And this transport infrastructure now have to evolve to support low latency and network slicing, and 4G is not going away. So solution like radio over Ethernet are needed to convert CPRI on Ethernet protocol, and therefore the operator are requiring a cost-effective, flexible, ubiquitous transport layer that can transport 4G and 5G traffic. And this is where a next generation xhaul converged packet-based transport approach for the frontal and the middle and the backhaul is becoming a very interesting option. But this comes with few new challenges. If we look at the result from an AV reading survey on the most challenging performance requirement for next-gen frontal network, we can see that packet-based latency measurement verification for ultra-reliable low-latency communication is ranking #1. Bandwidth throughput verification for enhanced mobile broadband is #2. Then we have the traffic priority and the profile verification for network slicing. And then the timing and synchronization verification, and eCPRI ORAN 7.2x interoperability and functional split verification. And this is interesting because this is all new challenges that was not really existing with CPRI, as CPRI was a synchronous interface with a fixed throughput and static latency. Why the latency being such a challenge? So obviously latency is key for 5G, and the latency requirement for the frontal is particularly stringent. So far, early 5G was mostly about enhanced mobile broadband, so the focus was not on latency. But as we are moving into the phase 2 of 5G, things are changing with a target to support new low latency services. We are talking here about a 10 to 25 latency improvement with a target of 1 millisecond end-to-end for URLLC. And this is a very aggressive target to meet that will impact both the RAN architecture and the transport infrastructure. So moving forward, controlling the latency of each network element will be very critical. And if we look at the latency breakdown for the frontal, there is a very stringent latency requirement of 100 microseconds between the RU and the DU. And this is even reduced to 25 microseconds to support some ultra-low latency use case. So considering that each kilometer of fiber will add roughly 5 microseconds, it adds up pretty quickly. And to achieve a 1 millisecond end-to-end latency for URLLC, it is critical to have much better control on the latency of each network segment, but also very critical to distribute critical mobile core function and services closer to the end user. So this is where edge computing come into play. It is also important that for the same transport network to be flexible enough to accommodate various services and use cases like enhanced mobile broadband and URLLC. And this is why new 5G transport solutions are now supporting network slicing capabilities. Quick word on network synchronization. So another key aspect to consider for next-gen transport architecture. 5G requires tight frequency and phase, synchronization in frequency and in phase to support advanced features like coordination multipoint, massive MIMO, carrier aggregation, beamforming. So but also because 5G is using TDD, time division duplex, instead of frequency division duplex. So we see a movement from GNSS receiver to network synchronization relying on 1588 PTP and SYNCI. And now that we are considering packet-based for the fronthaul, network synchronization is not just for backhaul anymore, as it can be extended to the middle and to the fronthaul up to the radio. So packet-based fronthaul require a different approach for test and qualification. Operators that are qualifying new transport equipment and preparing for first office application need to evaluate several new technologies and their impact on latency and reliability when they're putting together their test and integration strategy. They need to test the compatibility with 4G and 5G protocol. They also have a lot of new technology to validate, technology like radio over Ethernet and time-sensitive network, and technology for network slicing like segment routing and flexi. So important to validate that the traffic get the right priority, meet the latency requirements, and to validate that all the key quality of service KPI like the throughput, packet jitter, and frame loss are also met. Critical to validate the timing and synchronization aspect as well. Make sure that the transport solution meet the timing requirements and behave as expected under different type of synchronization failure. So possible to assess the performance of next generation transport solution by using test equipment that will replace the radio and the DU or BBU. Test solution that will generate a mix of 4G and 5G traffic like eCPRI, ORAN, eCPRI, and Ethernet to validate the reliability and the performance of a Converged 5G xhaul transport solution. Possible also for each traffic stream to monitor accurately all the key quality of service KPI like bit error rate, the latency, packet delay variation, and the throughput. And ensure obviously that the timing and synchronization aspect are met also and propagated correctly. So close to the end here, and before opening for question, I will close with this last slide on who is Exfo. So Exfo is the test, monitoring, and analytics expert with a complete end-to-end portfolio for 5G transport test solution, from everything fiber, for protocol testing as well, up to 400 gig, and for timing and synchronization validation in the lab, in the field, and for live 24/7 network monitoring. Thank you.
Thank you, Sebastien. That's really good. Kyle Milady was recently quoted as saying, well, actually it was a year ago, but recently quoted again as saying that 5G ultra wideband is really a fiber network with a bunch of radios at the end. And yeah. I thought that was great for our industry, our portion of it.
That was a good one. Yeah.
Yes, this is quite relevant. You mentioned a number of times, and I didn't see any questions coming in, so I'll just give you one. Precision time protocol. So, having both phase and frequency out to those antennas, we're finding that it's more critical than ever, and we're actually trying to make it the primary source, and that's because the antennas are so close to the street, to the end user, to everything else. Sometimes you can't get a good GPS signal, and sometimes it could it could be more easily blocked or something that are jammed than others. Are you seeing that in the industry? I mean, because again, that's so critical to 5G ultra wideband that
Yeah,
we're seeing a significant emphasis on it. Where before, like usual, timing was ignored or assumed. How's that? And it's becoming
yeah.
in center
So
lately.
so definitely it's a trend that we see everywhere. Something interesting from the US is that in the past, GNSS receiver was a bit more in usage, while we were seeing in Europe and in Asia more usage of network synchronization, 1588 PTP. But now this move to transition to 1588 PTP and to the 8275.1 profile, and in some case the 8275.2 profile, I can confirm that it's definitely worldwide. We get question requests if from all operators and equipment vendors, basically in all markets, all region. So this definitely seems to be a key topic and a transition that is happening now as we speak.
Great. I'm glad you guys are on top of it. Thank you.